Dear learners, in this program we shall discuss about a few selected applications of the theory of combination. Now, the applications which I will take up will emerge with the progress of the program. I am not spelling out the applications, but one important application would be a very simple proof of binomial theorem, and that thoroughly by way of reasoning. We would be hardly doing any algebraic steps, and the hallmark of the applications which I will be showing will be reasoning through which we will develop the concept of combination. Now, let us take up the first application, that is the value of factorial 0. What is the value of factorial 0? Now, we are aware of the relation factorial n is equal to n into n minus 1 into n minus 2, and we go so on up to 3 into 2 into 1, that is product of all integers starting from n. So, factorial 4 is equal to 4 into 3 into 2 into 1, that is 24. Factorial 3 is equal to 3 into 2 into 1, that is 6, and so on and so forth. But what is factorial 0? Now, before we go to the value of factorial 0, let me just recollect the idea of combination of n different things taken r at a time, n c r. Now, here precisely I have 5 different things: a wristwatch, an eraser, a pencil, a pen, and a piece of paper. Now, out of 5 things, if I want to select 3 things, so I can select the piece of paper, the pencil, and the eraser. So, I started with selecting 3 things out of 5 things, which I have done, but at the same time 2 things from those 5 things have automatically got selected. I did not make any effort for that, which means that the number of selection of 5 different things taken 3 at a time is exactly equal to the number of ways in which 5 different things can be combined into 2 different things out of that. Like, see, if I had selected instead these 3 things, then these 2 things get automatically selected. So, can we not say that 5 C 3 is equal to 5 C 2, and we can generalize that by saying that n C r, of course, n is greater than or equal to r, is equal to n c. Now, see 3 plus 2 is equal to 5. So, I have to write something here which plus r is equal to n. So, here I will write n minus r. So, n c r is equal to n c n minus r. Then what is n c n? N c n will be equal to n c n minus n, that is n c 0. And n c n, we can just apply common sense that we have n things, and in how many ways can we select n things out of those n things? We have 5 things, in how many ways can we select 5 things from 5 different things? Only one way. So, similarly, it can be generalized to any value n, and we can say that n c n is equal to 1. In other words, 1 is equal to n c 0, right. So, now perhaps we can explore the value of factorial 0. You know this result, n c r is equal to factorial n divided by factorial r into n minus r factorial. So, n c 0 is equal to factorial n divided by factorial 0 into n minus 0 factorial, which is again factorial n. So, you have factorial n in the numerator, you have 1 factorial n in the denominator. So, they cancel each other and you get n c 0 is equal to 1 upon factorial 0. But just now we have established that n c 0 is equal to 1, being equal to n c n. So, 1 is equal to factorial 0 in the denominator and you have 1 in the numerator. Therefore, factorial 0 is equal to 1. So, we arrived at the value of factorial 0 using the basic formula of combination. And there is another trick by way of which we can just apply the somewhat the principle of induction to arrive at the value of factorial 0. See, factorial n is equal to n into n minus 1 factorial. Let us put a second bracket here to bring more clarity. Therefore, factorial n divided by n is equal to n minus 1 factorial. So, to give further clarification to this, factorial 4 divided by 4 is equal to factorial 3. So, you proceed factorial 3 divided by 3 is equal to factorial 2 and then factorial 2 divided by 2 is equal to factorial 1. Have you observed? Every time what I am doing, I am dividing factorial n by n. It was factorial 4, I divided by 4 and the result is just n minus 1 factorial. Here it is 4, so it is 3 factorial. We continued in the same manner, factorial 3 divided by 3 is 2 factorial, factorial 2 divided by 2 is 1 factorial, and then you can definitely make out what would be my next step. If I repeat the previous step, we had factorial 2 divided by 2 is equal to factorial 1, and so factorial 1 divided by 1 is equal to 1 minus 1 factorial, our required 0 factorial. So, what is there on the left hand side? 1 factorial is 1, in the denominator you have 1 which is 0 factorial. So, 0 factorial is equal to 1. It may appear a little bit abstract, but you just think in that manner that you do not have anything at all and you have to arrange them. So, this is something unique. You do not have anything and you are arranging something out of it, and that is unique. The value is 1. The then next result, which we will establish by way of reasoning, is very common to you. N C r is equal to n minus 1 C r plus n minus 1 C r minus 1. Now, what is N C r? N C r is the combination of n things, n different things taken r at a time. Now, when you take the combination of n different things taken r at a time, then in every such combination you will find that one particular thing is always there or that particular thing is not there. Let us take the example of this pen, this die, and say this watch. So, you have three different things: the watch, the pen, and the die. Now, if you take a combination of two things, it can be the watch and the pen. So, the die is removed. So, in this particular combination, the die is not there. There can be two other combinations, that is the watch and the die and the pen and the die. So, in the later two combinations, the die was always there, and in the first combination it was not there. And if you take an aggregate of that, you get the total number of combinations. So, remember, one thing is always there and one thing is never there. So, if one thing is never there, then effectively you are selecting r things from n minus 1 things, because one thing is never there. So, that would be n minus 1 CR. And once that one thing has been taken with assurance, then the problem reduces to taking the remaining r minus 1 things from n minus 1 things, because one thing has already been taken. So, what remains are those n minus 1 things, and therefore, the next term would be n minus 1 C r minus 1. So, this can be proved by working out several algebraic steps, but without going into algebraic steps, just by way of reasoning you can arrive at the result, and a very, very fundamental and important result, that NCR is equal to n minus 1 CR plus n minus 1 C r minus 1. Had it been the case of permutation, well, again permutation of n things taken r at a time would contain these two kinds of combination. That is, in one particular permutation, one particular thing will not be there, and in the remaining permutations, that particular thing is always there. So, if one particular thing is not there, the number of permutation would be n minus 1 P r, and if that one particular thing is always there, then you keep that one particular thing and select the remaining r minus 1 things from n minus 1 things, and that would be n minus 1 P r minus 1. But here is a catch. Here your task does not complete just by way of selection. You have to make that one particular thing which you have selected to be arranged, and while arranging you will have to make r places, because there are r such things, and you place it in one of those r places, and by placing it one of those r places, the remaining permutation would be n minus 1 P r minus 1. So, for each of those r place, the permutation would be n minus 1 P r minus 1. So, for all those r places, the permutation would be r multiplied by n minus 1 P r minus 1. So, this can also be verified by working out the algebraic steps. So, we have arrived at two very interesting, important, crucial results of permutation and combination just by way of reasoning, without doing any kind of mathematical calculation, algebraic calculation. But again, I would repeat that the learners must verify this by doing the algebraic calculation. Now, what is the implication of the first result? Now, let us take a specific example. Let n be equal to 2. So, the result is NCR is equal to n minus 1 CR plus n minus 1 C r minus 1. If n is equal to 2 and r is equal to 1, you get 2 C1 is equal to 1 C1 plus 1 C0. So, in effect, you have written 2 C1 is 2, 1 C1 is 1, 1 C0 is 1, 2 is equal to 1 plus 1. Similarly, 3 C2 is equal to 2 C2 plus 2c1. Again 3c2 is 3, 2c2 is 1 and 2c1 is 2. So, where does it find application? You remember I have written a very known result 2 is equal to 1 plus 1. I have given it a little color using the theory of combination. 2c1 is equal to 1c1 plus 1c0. Again 3 is equal to 1 plus 2 and I have written that by applying combination. I have written 3c2 is equal to 2c2 plus 2c1. So, let us create a tree like this. At the top of the tree I keep 1, I maintain this series of 1s on the two sides. This can be further expanded. Now, let us do this for these 4 lines. 1, 1, 1, 1 plus 1 is equal to 2. So, let me write this 2 here. 1 plus 2 is equal to 3. Again you read this as 2c1, you read this as 2c0 and 2c1 plus 2c0 is equal to 3c1, that is as good as saying 2 plus 1 is equal to 3. You could have taken one more step, write 1, 1 plus 3 is equal to 4, 3 plus 3 is equal to 6, 3 plus 1 equal to 4 and then again you get this 1. So, you get a triangle and this triangle actually carries the coefficients of binomial expansion. See, a plus x to the power of 0 is equal to 1, a plus x to the power of 1 is equal to a plus x. The coefficients are a and x. Now, a plus x whole square is equal to a square plus 2ax plus x square. So, 1, 2, 1. A plus x whole cube, what would have been a plus x whole cube? That would have been a cube plus 3a square x plus 3a x square plus x cube. So, the coefficients are 1, 3, 3, 1. See 1, 3, 3, 1. Let us see the growth of this triangle. 1 plus 1 equal to 2. So, this is the reflection of 1c1 plus 1c0 equal to 2c1. Then here 1 plus 2 equal to 3. So, this is the reflection of 2c2 plus 2c1 equal to 3. Then again 2 plus 1 is equal to 3. This is a reflection of 2c1 plus 2c0 is equal to 3c1, that is equal to 3. Similarly, here 1 plus 3 equal to 4. So, that is a reflection of 3c3 plus 3c2, that is equal to 4c3, or 4c3 is equal to 4. Similarly, here you will get 3c2 plus 3c1 is equal to 4c2 and 4c2 is equal to 6. So, that is how the triangle grows and this is called the Pascal's triangle. In fact, the entire binomial coefficients can be obtained from this very triangle called Pascal's triangle. So, this is a very convenient way to present the binomial theorem, and by following this you can derive the general form for a plus x whole to the power of n. But what we will see finally, how this can also be obtained by way of pure reasoning. See, a plus x whole to the power of n, that is what we have to determine, is a plus x into a plus x and so on up to n times. So, there are n brackets and each bracket contains a and x, a ones and x ones. Now, let us multiply two binomials a plus b into c plus d. You can very well make out that there would be 4 terms. Which are those 4 terms? AC plus AD plus BC plus BD, is not it? AC plus AD plus BC plus BD. Now, examine each terms. Let us examine AC. A has come from the first bracket and C has come from the second bracket. AD, A has come from the first bracket, D has come from the second bracket. BC, B has come from the first bracket, C has come from the second bracket. BD, B has come from the first bracket, D has come from the second bracket. So, each term has contribution from each bracket. There cannot be a term which has contributions from one bracket only, the other bracket contribution being totally absent. It cannot happen like that. Every term contains contribution from each bracket. So, in this expansion also a plus x whole to the power of n, every term would be having contribution from every bracket. And what has these brackets to contribute? The brackets would either be contributing a or it would be contributing x. Now, if each bracket contributes a, the term would be a to the power of n. And how many such terms? That would be the coefficient of a to the power of n. Now, in order to count how many such terms, the theory of combination comes into play. There are n number of a's, n number of x. So, you are selecting n a's from n a's, or in other words, you are selecting 0 number of x from n x. If you are selecting n a's, that means you have selected 0 number of x. So, 0 x from n x, and that can be done in n c 0 ways. So, the coefficient of a to the power of n is n c 0. The next term would be such that there would be a coming out of n minus 1 brackets and x coming out from 1 bracket. So, that would be a to the power of n minus 1 into x. And so, out of n brackets, 1 bracket would be contributing x, and so in effect you are selecting 1 bracket out of n brackets, which can be done in NC1 ways. So, this is NC1 a to the power of n minus 1 into x. Similarly, the next term would be n minus 2 brackets contributing a and 2 brackets contributing x. So, 2 brackets out of n brackets contributing x, and that would be NC2 a to the power of n minus 2 x square, and so on and so forth. The general term would be NCR a to the power of n minus r x to the power of r, and final term would be x to the power of n, where all the n brackets would be contributing x, like here all the n brackets had contributed a. So, all the n brackets had contributed x, no bracket has contributed a, and so that coefficient would be NCn, which again is equal to 1. So, this is your good old binomial expansion. A plus x whole to the power of n is equal to a to the power of n. I am not reading NC0 because it is 1, a to the power of n plus NC1 a to the power of n minus 1 x plus NC2 a to the power of n minus 2 x square, the general term being NCR a to the power of n minus r x to the power of r up to x to the power of n. Finally, let us write this expansion. A plus x whole to the power of n is equal to a to the power of n plus NC1 a to the power of n minus 1 x plus NC2 a to the power of n minus 2 x square plus NC3 a to the power of n minus 3 x cube plus so on. The general term is NCR a to the power of n minus r x to the power of r and so on, and finally up to x to the power of n. So, a plus x whole square, a square, n c 1 would be 2 c 1, a to the power of 2 minus 1, that is 2 a x plus x square, a plus x whole cube, a cube, then 3 c 1, 3 a square x plus 3 a x cube plus x cube. A plus x whole cube would be a cube plus 3 c 1, that is 3 a square x plus 3 c 2 a x square. So, that is 3 a x square, then the next term would be x cube. So, using this formula you can derive any power of the binomial a plus x. But the beauty is that here we have made the derivation purely by applying the theory of combination and also by way of reasoning only. Hardly we have worked out any particular algebraic step. So, what we have studied? We have studied a few applications. First is determination of the value of factorial 0 and to remove the aura about the abstraction associated with factorial 0. We have seen the derivation of a very common formula NCR is equal to n minus 1 CR plus n minus 1 CR minus 1, and that again thoroughly by way of reasoning. We have applied that to create the Pascal's triangle, and then we have extended that to prove the binomial theorem. That is, we got the essence through the Pascal's triangle, and then we also proved it thoroughly again by way of reasoning. This is to sensitize you about the fact that the theory of combination and along with that, that of permutation can be understood very well mostly by way of reasoning. Your strategy would be to apply reasoning as much as possible and to use algebraic steps to the minimum, and then only we will feel that this program of ours has been successful.
हिंदुस्तान के हर कोने में नौजवानों के पास प्रतिभा है, उन्हें अवसर चाहिए।
NIOS देता रहा है युवाओं को अवसर आगे बढ़ने का। NIOS से पढ़ने वाले इन युवाओं ने किया है संस्थान को गौरवान्वित। दिव्यांगों ने बन के दिखाया है सबल और आत्मनिर्भर। NIOS के साथ आप भी जुड़िए NIOS के संग।
जीवन ये प्रकाशित करने, राहों को आलोकित करने, हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने। जीवन ये प्रकाशित करने, राहों को आलोकित करने।